Hello everybody and welcome to today's session on one day in the life of a nuclear power plant operator. My name is Dr. Jo Lackenby. I'm the President of the Australian Nuclear Association, or the ANA. Today's event is co-hosted. So our co-hosts are Women in Nuclear Australia. So very special welcome to my co-host, Jasmine Diab from WIN. Today's event wouldn't be possible without the help of two organisations. So a big thank you firstly to AINSE for letting us use this wonderful venue, and also to ANSTO for organising a lot of the logistics for today, especially Susan and also Rod. Thank you very much. I'd like to ask Brett Rowling to come to the stage. He is a Guringai from the Guringai mob, and he's going to give us a discovery and understanding of country.
Alrighty, we'll go something a little bit national. So we have these things, they're called totems, a very westernised way of speaking, but a totem is basically, it's something that you're born with, and it's going to be something you look after for your life. So of course you would all know mine's Darryung, and of course you'd know exactly what that means. That's a stingray. So what you've got is if you go around different parts, well, ANSTO has its own totem piece that we've laid out as well, which is the emu, and it's something that, it's a national piece, because every mob has a story that goes with it, and some is a physical sort of story. So in Central Australia, it follows the life cycle of the emu. So there's certain times the male actually looks after and raises the chicks, but while he's sitting on the eggs, you can go and get yourself one and have an omelette. If you go to Western New South Wales, it's a story it teaches you morals, because since the beginning of time you have emu and bush turkey have this argument that continues right the way through, and emu loses his wings because he gets tricked, and in the course of losing his wings, he now can't fly anymore. Now, because of that, he's being taught that you can't really get too far ahead of yourself at any part in your life. And if you go to the far south coast, you end up with the people down there. The women actually wear a piece of kangaroo skin with the fur, and what it does is that when the fur is visible, you can see the emu, because the emu's in the sky for them. They look at it, it's an emu dreaming. And when the emu disappears, because of course as the earth revolves around, they spin this around and now it's just the skin. If you go to where my people are, he is male for us, and twice a year he points to the ocean, and that's the point in time where it's basically our bookends our fishing season. So fishing through summer season, but in the winter we moved inland, and the idea of that is to preserve the fish stocks. And of course, because it's in the stars, or Kalang, our words, meaning that's where our ancestors go and live, it's a spiritual connection that anyone can see right across country. I suppose we could even connect to Nipissing people as well from up in over in Canada as well. So I think with that, and the third thing that goes with it is the fact that these stories have... I'll leave it at that. Oh, go on.
Emus to nuclear energy. I've got nothing, sorry. Just a reminder to anybody online, welcome. Please put your questions in the Q&A. So I was fortunate to attend the Women in Nuclear Canada conference last year at Niagara Falls. And I had the pleasure of meeting today's speaker, Tracy Primeau, at the bar. It's definitely an Australian and a Canadian way of meeting people. She said to me, I'm coming to Australia in April and I'd like to give some talks. So here we are. Woo. So Canada has a thriving nuclear energy industry. Their CANDU reactors are being refurbished, and this will extend the life of these plants for decades. There's also strong plans and government support for a rollout of small modular reactors. I hope this isn't a spoiler, Tracy, but the province that Tracy is from, Ontario, has possibly the lowest carbon emissions out of any large grid in the world, and it's dominated by nuclear and also hydro. So Australia has a 25-year ban now on nuclear energy. As energy security and climate change becomes more and more pressing, nuclear energy is definitely something that's starting to be talked about a lot more in Australia. So just say Australia decided to build some nuclear power plants. What exactly is it like to work at a nuclear power reactor? So today we're going to find out. Tracy Primeau wears many, many hats. She is a board member of Ontario Power Generation and other organisations. She's a wife and a mother. She's a proud member of the Nipissing Nation. She's worked for over 30 years in the energy sector, including as a shift manager at Bruce Power. Here she worked her way up from the shop floor with a trades degree up to become a shift manager, which is actually a very, very remarkable achievement. I just want to give a quick special shout out to anyone today who works at the Opal Reactor, in particular the shift managers and the reactor operators who are watching today. So without further ado, over to you, Tracy, for your presentation on a day in the life of a nuclear power plant operator.
Thanks, Joe. Thanks, Joe. So, hello again, Ani Bozu, Tracy Nipissing Indujba, Magizi Dodem. Magizi is the Ojibwe word for eagle, which is my totem, as Brett discussed the totems here in Australia. We refer to North America as Turtle Island. So it's all of the First Nations in Canada have a very strong connection to the turtle. So today I'm going to do a tour through the plant. I'm going to try to make sure I leave lots of time for Q&A. I'm hoping that you have lots of questions either that you're coming with or that come up as I'm speaking. Please make note of them. I'm going to just start with a little bit with how my story starts. So I went to the University of Waterloo, and I was going to be a history teacher. That was my plan. Fortunately, the University of Waterloo gives you opportunities to try out different careers, and I got to spend some time with high school students and decided that was not the life for me. So my father worked in the nuclear industry, and he encouraged me to apply to be an operator in training. This was in 1990. Women had only been allowed in the nuclear power plants for 5 years at that point, from 1985 on. So they were really trying to increase their workforce and get some diversity. I did end up with that arts degree, and I started at Pickering in 1990 as a field operator. In 1995, I transferred to the Bruce site, where I spent the rest of my operations career. And so when I was a field operator, my day would start like this. This is my locker at Bruce. I have been retired for almost 2 years. These pictures are not from 1995. They're from probably 2019. So once you get into the change room, you remove all your civilian clothing and you put on coveralls. And that includes undergarments. So the undergarments are supplied basically so you don't have to wear your own, although that is an option. And everything can be laundered there on site. When I started, we wore browns, and there was only men's underwear and tank tops available to the women. No bras or female underwear. Although I kind of got used to those briefs, to be honest with you. They were quite comfortable. Other changes were, and I'm going to mention this now because I'm talking about protective equipment. We have a expectation to pee in a cup. At that time, when I was field operator, it was weekly. Now it's kind of based on the work you do. And the top of the cup was this big. I don't know if people online can see. And so obviously it was not made for women. And, it never occurred to me to complain. And then about 10 years ago, they redesigned it. So now it's this big. And I thought, what a great idea. How come I never brought that up? But someone did. And it's just a sign of the changes. The personal protective equipment coveralls were not made for women. And over time that has changed. The undergarments, even the actual work boots, where you pick them up at the storekeepers, and and hope for the best. Hope that you were going to get a pair that actually fit you, or you wore double socks. So I just wanted to mention that has changed it. We have, as I mentioned, when I started, we wore brown coveralls, and we had to take them all off to go have lunch or coffee. And but now with the better contamination control processes in the nuclear power plants across Canada, we put on a pair of blues and we can wear them all day, out to the cafeteria, out to lunch. Obviously, we monitor. There's just such good contamination control now between zones that it's no longer required that you shower every time you go out for a meal. So that has been a really nice change for operators. So I always look for the softest pair when I'm putting them on, because I'm going to be wearing them for a long time, and that all the pockets don't have holes in them. I've lost many TLDs, thermoluminescent dosimeters. We use the acronym all the time. You forget what it means. Through a hole in the bottom of my coveralls. So here I am, getting ready for a walk in the plant. You also want a big pair because you want to have some room for all those things you're going to carry in your pockets. So the PPE, as I said, includes those coveralls, hard hat, safety shoes, glasses, ear protection, a TLD, and an EPD, so electronic personal dosimeter, that would alarm if you went over a dose rate or a dose actually picked up too much dose. The TLD is monitored once a month to see what you've picked up over the last month. As I mentioned, we also do a bioassay. It used to be weekly, but now it's based on the work you do. So, on this day, I was going to be going into a radioactive area, so it would require me to make sure that I put a bioassay in before and after to see if I had any uptake from tritium or particulates. And then also we do whole body counts at least once a year, basically standing in a large counter that just goes around you and is checking for all those other things, alpha and carbon-14, things like that we can't measure in any other way. It used to be when I started at Pickering, you laid down and it was like a coffin, and they closed it over you, and they had a lot of people have like claustrophobic events. So now you just stand in it like an airport scanner, and it just goes around you. Personally, I don't have a problem with claustrophobic, so I would just have a nap. The operator toolkit that we give to every operator that comes to join us, it's usually a fanny pack, although you can use it however you want, and includes things like a multi-tool with a knife and perhaps a little screwdriver, a crescent wrench, a fuse puller, a potential tester, a radio, a special key that allows you to open certain rooms in the plant. And most of the operators either carry that in a fanny pack or put it in their pockets, so they have everything they need as they're walking around. I am going to talk about a bit of a change for that as well. So now I'm ready to go into the plant, and the first pump I come to see is a boiler feed pump. So this feed pump is really important to the turbine side of the plant. So I think a lot of this turbine side will be very different from what you do here at Opal. So the reactor side has many similarities, but what we call the rusty side, the secondary side, I think will be quite different. So we need three of these. We have three of these pumps. We always need, they're 50% duty, so we always have to have two running when we're at full power. And the field operator is the eyes and ears of the control room. We're going to talk about the control room operator. That's another job I did. And I know it's a job that you have here at ANSTO. But we really need that field operator out in the plant looking at the things we can't see before they bring an alarm in. So these pumps, we need two always running. They take water from the deaerator at the top of the very of the plant, of the turbine building, and pump it up to the boilers. So all the way down to what we call 591. We measure our floors by sea level feet at the Bruce site. 591 is, I had to do the math, 180 meters above sea level. That's what the elevator says. You know, it's not 1, 2, 3, 4. It's 591, 615, 639. The newest plant, the Darlington plant, uses meters. But when Bruce was built, we hadn't converted to metric yet. So every shift, you know, I expect an operator to use all of their senses when they're walking around this pump, listening to it. Does it sound right? Is there a weird smell? Touching it as well, checking for temperature. You know, we teach operators to always touch a pump with the back of their hand so that the natural reaction is to pull it away from you rather than with the front of your hand where you're more likely to get a burn. And just around the time that I was taking these pictures, there had been an operator who had been in, you know, a couple shifts. We work a shift schedule, 2 days on, 3 days off type thing. He had been in a couple shifts before, and he noticed when he came back in to do his rounds again on this shift that there was a little change in the water that was in the oil reservoir. So sometimes we do get a little condensation in the oil reservoir, but there should not be water in it, and it can damage the pump. And so he brought it to the attention of the control room. We were to safely take that pump out of service, put another one in service, and without having to do it, you know, in a moment of anger, like, oh, we have to do it now. We have to put the standby in without checking everything, shutting down appropriately. And that's the kind of thing that we really count on operators to find and make note of. And that's what we call their rounds and routines. I know you have a similar thing here at the reactor at ANSTO, and there will be on every unit operator who just looks at the turbine side and an operator who looks at the reactor side, and they're looking at all of the equipment they can access and making note of any changes, pressures, temperatures, and leaks, all that kind of thing. So we're really counting on them to see the things that we can't see from the control room. This next piece of equipment is the turbine oil purifier, and it's really important that our turbine oil is as pure as possible. Any impurity, whether it's water or some sort of particulate, can trip the turbine or damage the blades. And so this oil purifier is taking out, it's like a centrifugal force, taking out the water. And we're actually checking this one more than once a shift because it's so important that we're collecting all of those impurities. And the turbine lube oil is directly tied to the generator seal oil. So the turbine lube oil keeps those bearings lubricated, and the generator seal oil keeps the seals full of oil so that the hydrogen does not escape into the turbine building, which of course would be a very big fire explosion hazard. So this is on the secondary side, one of the most important safety parameters that we have to monitor. Stator cooling water pumps is also tied to the turbine, so the stator is part of the generator. And we need to keep the hydrogen in the generator cool. Here we have some chain-operated valves. They're quite common in older plants. You know, they would be a bit too high or complicated to get to with a ladder, so we would chain-operate them. As a smaller woman, when I started my career, I found it very hard to operate these valves. So what I would do is I would stand like on the pump beside it, jump, grab the chain, and use my body weight to close the valve, and hope no one was watching, basically. So now we do have easier ways to get to these valves and better persuaders to help anybody of any height or strength to be able to pull these chains. You know, they would just get stuck at the top, and it would be really hard to get that first pull going. Every pump and valve and breaker has a flow sheet in the station, and quite often those flow sheets are actually, you know, right around the corner from the pump. So if I was out walking and I was concerned about the lineup. I could look at the flow sheet around the corner and see what position that valve was supposed to be in. So the flow sheet will show both normal alignment and off-normal alignment. So normally you have to have, for example, one of these pumps running and one of these heat exchangers in service, and the other pump isolated, but the other heat exchanger available. So you could check those on the flow sheet. Now, keeping those flow sheets updated in the field was an extra task for our business support staff. And now what the field operators have is they have a tablet that they just carry, so something else in their tool bag. And the Wi-Fi is improved enough around the plant now that they can just type in the flow sheet, bring it up, zoom in on what they need to see. And not only does it tell them what it should be, but it'll also tell them if there's something broken or there's an isolation for maintenance. So it's quite updated from when I was in the field. I just wanted to show the graded flooring. A lot of people struggle with graded flooring. I know I've been on some tours with people who aren't comfortable with that look. This is the boiler stop valves. There's a lot of graded flooring in the plant, both on the turbine side, this is where this is, and inside the vault. And the great thing about graded flooring, though, is you can really feel the vibrations of the unit on the graded flooring because of the way it comes together. So when a unit is going up in power or coming down in power, or something just doesn't sound right with the turbine, you can really feel it in your feet when you're walking around on the graded flooring. So this is another example of one of the senses that you get to start using when you've been an operator for a while in the field. I was always in operations, even as I moved into the shift management role. And so I always had a good feel for what this vibration should feel like on each different unit, because they're each a little bit different. And Unit 3 was my unit for a long time as a field operator. So that one in particular, I really knew what sounded normal and what didn't. This is the overhead picture of the Unit 1 turbine at Bruce A. There's 4. So the steam comes through those valves I just showed you into valves that control it through the high pressure turbine. It is then heated up and put through the low pressure turbines, which are these 3 large yellow things you see here. At the very end, it's attached to the generator. So the steam turns the rotor and from the the high pressure turbine through the low pressure turbines, turns the generator, and then the rotor and stator interreact with the electromagnetic field, and we make electricity. So for a long time, the Bruce site was the world's largest generating station as far as megawatts. It's between 850 and 900 megawatts per unit. There's 8 units. So it's just under 7,000. But there's one in Korea that's 7,500 now, and I think there might be one in China. However, we are the biggest site area-wise. We are almost 1,000 hectares. Across the site, there is 2 stations with 4 units each, Bruce A and Bruce B, 67 kilometers of roads. We have a full emergency response team, a full security team, as big as the city of Kingston, which is one of our larger cities in Ontario. We have doctors, we have nurses, we have physiotherapists. We have full support services for IT. There are about 7,000 people that work at the Bruce site, and really, I often say to people when they ask me about getting into the nuclear field, they'll say, I don't know anything about engineering or science, and I'm like, you can do anything in the nuclear field. We have a job for everyone. If you're a great communicator, you're great with people, you want to work in marketing or anything you can imagine, we have that happening in the nuclear industry. So I'm going to start moving to the, well, not totally, but I'm going to start showing you a little bit about the reactor side, the shiny side, we call this. And these are the heat transfer pumps. They're the biggest pumps that we have. They are 8 kilovolts, powered by 8 kilovolts power. And the heat transport system is full of heavy water. Heavy water was created in Canada. In fact, the heavy water used at HIFAR came from Canada. And we use it to cool the fuel as well as to moderate the nuclear reactions. That heavy water goes through the heat transport side and cools the light water that goes to the boilers. So in this way, our style of reactor is a separation between the fuel coolant and the steam. There is no tie between them. Whereas a boiling water reactor, which is a very common reactor in the US and Europe, that uses the same steam that goes through the reactor to turn the turbine. So the turbine has to be well contained. The CANDU is not that design. It's totally separate. So there is no radiation on the turbine side. It's considered zone 2. Only the reactor side is considered zone 3. There are 4 of these pumps in each unit. Back in 2017, so these pumps, these are the pump motors you're looking at here, but underneath them are the pumps. And the pump bowl itself is outside containment, but the loop is inside containment. In 2017, we had a pump seal fail at Bruce A, and so we had a heat transport leak outside containment. The operators, again, were amazing, responded to the leak, contained it, signed the appropriate areas. The control room obviously shut down the reactor, shut down the heat transfer pumps, and the field were really heroes of the day in controlling that leak. This particular type of leak is trained for in the simulator, but this particular incident ended up being a great lessons learned for the entire industry. And the actual cause of it turned out to be a legacy issue with a bad seal that we had bought from a manufacturer 25 years beforehand. So it was a real good, and that's one thing I do want to mention while I have an opportunity here. The nuclear industry is excellent at sharing their knowledge. We have had too many bad news stories to not do so. So, from 3 Mile Island to Chernobyl to Fukushima, we have to share our lessons. After 3 Mile Island, IMPO was created, the Institute of Nuclear Power Operators. After Chernobyl, WANO was the World Association of Nuclear Operators. And in both those cases, those organizations, IMPO and WANO, go to every nuclear plant in the world, evaluate them, offer them support and help if they are performing at the lower end, and use them as examples that they're performing at the higher end. Both Bruce A and Bruce B are considered WANO 1 stations, which means they are exemplary. The same is true for Darlington. So lots of people from all over the world come to our plants to see how to do things well. And I would say, compared to oil and gas or other industries, no one is sharing that information the way that we are, because we know, well, there's a great book called Hostages of Each Other. We know that if one plant fails, we all feel the repercussions of it. And so we're very committed to helping each other be better. This is the main output transformer. The electricity leaves that generator I showed you. It is either stepped up through a transformer to 230 kilovolts or 500 kilovolts, depending on what unit it's coming from, off down the grid to Toronto. And we are supplying from the Bruce site much of southwestern Ontario, because we are making the most megawatts in Ontario, but also there is Pickering and Darlington closer to the GTA, to the Greater Toronto area, that are supplying power as well. I want to talk a little bit about work protection because I know you do this here too, or tag out or lockout. I'm not sure what phrase you use. One of the most important things operators do is make things safe for maintenance to work on equipment. So it's very important that we lock out, tag out anything that a maintainer is going to work on. For example, let's say we need the mechanics to change the seals on that boiler feed pump I showed you at the very beginning. We need to make sure all of the electrics are isolated. We need to make sure all the valves are closed in the proper area. The vents are open, the drains are open, and that pump is completely safe for that maintainer to work on, knowing that there will be no energy introduced into their situation. So what we do here is we have a real defense in depth way. We start with an operator preparing the work protection, another operator checks it, another operator applies it, another operator verifies it, and then maintenance walks it down. If it's a really important work protection, like a large condition guarantee for an outage or a reactor shutdown guarantee, the shift manager walks it down. And that's what I was doing this day. I took these pictures in blues. I was going to walk down a reactor shutdown guarantee on an outage unit because it's so important that you have that extra step of verification when it's about the reactor or a very large isolation. And this is probably the number one thing we do in support of conventional safety, industrial safety, as operators. Obviously, reactor safety is our number one pillar, but the day-to-day work, I feel this is one of the most important things that we do, and we need to do it well. We also lock valves. So I showed you some breakers. We also lock valves. So we either use a chain, or if it's a smaller valve, we put like a yellow donut on it. Not like a Homer Simpson donut, but like a plastic little thing, and we lock that up so that no one can operate those valves. And then this is a condenser makeup valve, and I'll take this opportunity to tell a story. In December of 1994, I had just come back from maternity leave after my first son was born, the one who lives here in Australia, and we had a leak in the boiler room at Pickering Unit 2. I was still working at Pickering. So at the end of the year, you get close to your target dose, which at the time was about 1 rem in 1994. But I had just come back from mat leave, so my dose was really low. And they needed some people to go into the boiler room and isolate this leak. So I went in with a couple of control room operators, also who had low dose, to isolate this, I mean, I don't want to call it a loca, but it was a pretty big leak. So we went in, and the interesting thing was, we went in and we found the leak, and we closed the isolation valves. It was a pipe that actually broke, so it needed a manual intervention. But the interesting thing was on the secondary side, because there was so much extra heat created, the condenser tank overfilled. And so it was actually raining in the stairway. As we walked up to the boiler room to go in, it was light water. There was no danger. But, you know, it just shows you how everything's interconnected from the reactor side to the turbine side. And you have to understand that interconnection to understand the hazards and the diagnosis. And that is, I'm going to get to that when I talk about the control room training and the shift manager training. This was December, I think, I want to say 16th, 1994. And it happened to be the night of the Pickering Christmas party. So all of the managers were gone and not really available for good advice, I guess, at the time. So we have 4 reactor units, as I mentioned at Bruce A, 1, 2, 3, and 4. And then we have a common unit. This is just a picture to get me to focus on talking about that. This is the path to the vacuum building, containment, and fuel handling. So fuel handling. So we fuel online in the CANDU, which is unique in the industry. And it is really, I think, one of the most incredible inventions in the Canadian nuclear history. So what we do is we take these bundles, we use a hoist to lift them and put them on a conveyor because they're about 35, 40 pounds. Oh, I looked that up too. 17 kilograms. and we put 16 in a fueling machine. It's like a magazine that goes around. And we put them in the reactor. The spent fuel comes out another machine, and we bring it to the bay. So this, in theory, and I want to say in theory because it doesn't always happen, would allow us to run for 3 years without a shutdown. And that is the goal. Once all the refurbishments are done at the Bruce and Darlington, is to get to a 3-year cycle where we run for 3 years, shut down for 30 days, and do the maintenance we need to do. However, things break, and including fueling machines. And at the Bruce and Darlington, we can fix them online, but at Pickering and New Brunswick Power, they have to take the unit down to fix them because they're a bit different design. So in theory, there is a unit that has run for 650 days in Ontario. It's one of the units at Darlington, might even be 700. There's one at the Bruce that's run for more than, or up to almost 2 years. So it is, the theory was we're going to fuel online so we don't have to shut down to fuel, like you do here at the Opal, and like most pressure-wise water reactors and boiling water reactors do around the world. So that is, I think it's one of the coolest things. It's one thing that when I go talk to other power operators, they really want to know about. We use natural uranium in Canada, uranium-238. We do not enrich it at all. And the reason that we can do that is because we use heavy water as our moderator and as our coolant. So it slows down the neutrons enough that we get enough fissions for the little bit of U-235 that's in that natural uranium. And that is also unique in the industry. Most reactors enrich somewhat, up to 20%, which is low enrichment. We've never had to do that with CANDU. So the machine goes in the reactor. It stays for 6 to 12 months, depending on where we put it. So if it's right in the middle, it's going to burn up faster. If it's at the outer edges, it could be even more than 12 months, going to burn up slower. And then it comes out of the reactor, it goes to a pool. It's a smaller pool, then it goes to a larger pool, and then it goes into giant concrete casts. And all of the fuel that has been created at nuclear plants in Canada is stored on the sites where it was created, much like you have your waste stored here at Opal. And there will remain until we have a path forward with the Nuclear Waste Management Organization on where we're going to put that fuel long term. So all the nuclear waste created in Canada would, I don't know if this is going to work in Australia, would fill about 7 hockey rinks up to the boards. I don't know if you can picture that. I should have done like a football reference or something. And all of the fuel that you would ever use in your entire lifetime, if you used every single kilowatt of electricity from nuclear, would fit in a soda can. So the amount of waste we are creating for the amount of energy we are making is very small. And I think that a lot of and so nuclear plants have been running since the 60s in Canada, and 7 hockey rinks up to the boards. We also do have new reactors being designed that have the opportunity to use some of this fuel. Recycled molten salt in particular, and there's one in New Brunswick. So, there's options about using this fuel, and there's also a lot of, there's been a lot of long conversations with local communities and Indigenous communities about the storage of this fuel, which is high-level waste as compared to the waste you have here at Opal, which is intermediate. So this is me. I'm going into the fuel handling area. So we have every 12 years a station containment outage, and we shut down every single unit. And we cool them down, and we depressurize containment so that we can go and make sure containment's working. And what we do is we pressurize containment. So containment works at a vacuum. It's like your vacuum cleaner below atmospheric pressure, and just a little bit below, like about 3.5 kPa. So what we do is we depressurize it and we pressurize it up to 70 kPa above atmosphere, and then we walk around with giant like backpacks full of leak tech, and we spray every single crevice in the entire plant that has a containment opening, and we look for leaks. Everybody on site comes to help with this. You're an HR, you're business services, you're an ERT, you are coming and you're helping with this. It's about 12 hours, and it's 700 to 1,000 people in the station walking around with this leak. They do a little bit of training, and they walk around and do this leak. So there was one spot in the fuel handling area where they needed to go into a room with some leak tech. There was no hose. I'm going to show you a hose in a minute to connect to a plastic suit. So whoever had to go in had to wear a firefighter SCBA, which I had been on the fire brigade as a field operator, so I had that qual. And they had to be green qualified, which is the highest level radiation qualified. 750 people in the station, and the shift manager is the only person with these two quals. So this is what they did. They suited me up in Tyvek with the SCBA hood, and I really was in the room for a total of 3 minutes, and checking for leaks, and came back out. But this is an example of outage focus. So we don't have outage focus like they do in the U.S., where a unit comes down to refuel and everybody comes to help. Because we have 4 units at each site, we could be in an outage at any time. But when we have a station containment outage, it's all hands on deck. Everybody is there. Everybody is helping, from the CEO to the brand new operator in training, and we try to get these done as quickly as possible, because the longer we're shut down, the less money we're making. And the last time Bruce did one of these outages, it was record-breaking 23 days. So that was from the first reactor shutdown to the containment checks to the last reactor coming back up, which is an impressive timeline. So here we go. We're going in the vault. So during the Unit 1-2 restart, we did a virtual tour. So I took a couple screenshots of that tour. And that's why Mike here is not wearing a full plastic suit, because the fuel was removed from the reactor, and as well as the heavy water. Well, we did the refurb, so there was very little tritium or contamination concerns. He is wearing an air purifier for any particulate for the welding that he's going in to do. So this is an airlock. I just got to go through the airlock in HIFAR, and it's not that different. You open one door and close it before you open the next door. You can do it automatically or manually. Normally we do operate them manually during an outage, because they are operated so often, where we need to really watch the seals and the equipment as we go through. And so he's entering at the 639 elevation. I have no idea what that is in meters, but it's basically the 4th floor in the station. And here he is. Here we are through the airlock. You can see these fellows back here are wearing plastic suits, and you can see the red hose on the bottom of the screen. So there's an air header in the vault. Air headers in the vault. You grab a hose, you plug into it. It pressurizes your suit, so you're under positive pressure. It's like a Michelin man. It's actually very cool, which is lovely, because when you're walking in, it's very hot until you plug in. And it also has your communications in the same cable, so you can talk to each other. and you can talk to the control room, and you can talk to the airlock desk outside if you have any issues. So that communication and hose is all gone together. This positive pressure means that you're not going to inhale anything because you're under positive pressure. If you have to unplug and move from one place to another, then you want to move as quickly as possible and plug back in so you keep that positive pressure up. I think that this is where you fixed my slides for me. Yes. So this is the reactor face. There's 480 channels in each CANDU reactor. So in each of these channels, 12 of those fuel bundles we saw a little while ago, or 13, depending on the design, go into these channels. The fueling machine goes up and down the face, putting the new fuel in on one side and taking the spent fuel out on the other. So it's like a matching pair on each side of the reactor. We also use the fueling machine to move people. So in an outage, we have to go up and down the face to look for, check our fuel channels are still healthy, doing a scrape, checking that the springs haven't moved. Sometimes we do something called a lithium lick, where we clean the lithium off the end of the end fittings. And so we will use the fueling machine with a giant platform to move people up and down the face to do their inspections and or repairs. And that is all controlled from the control room. I'm going to try and show you a decent picture of that shortly. As I mentioned, this is obviously a picture during an outage, but these machines would be going up and down while we're online. As I mentioned, we fuel online. Now, the new small modular reactor that we're building in Ontario will be different design. It will be a boiling water reactor, and we will be shutting it down to fuel. However, due to the size of that reactor and the type of fuel, it won't be a 30 days run, 5-day shutdown like the OPLAs. It'll be, a couple years of run time before we have to do any refueling. So underneath the bottom of the vault, we have what we call the fuel machine duct. And this is what the fueling machine runs along. So when the fueling machine comes down off that reactor face, it goes underneath all of the reactors and back to that bay where it dumps that fuel. Now, Janet, you were talking yesterday about time in air that the isotopes could have, or...
How much they need to decay before they can come into the air.
Right. So when we dump the fuel, there's a certain amount of time when they come out of the machine. We turn the carriage and bring it down into the bay. And that time that fuel is allowed to be out of the water is 7 minutes. So the fuel handlers have to be really well trained, even though it's not a reactor operator position per se. They are very well trained, have a simulator, just like the reactor and Unit 0 people do, to make sure that they not only can operate the fueling machine safely and correctly, but are prepared to respond to an emergency where, for whatever reason, that bundle wasn't discharged correctly. They often feel like they don't get enough attention. Oh, I thought I should mention them. And here's Mike heading back out. We have multiple airlocks in the station. Airlock 5 is a small airlock, as is airlock 2. But then we have a giant equipment airlock, so we can move in those big pieces of equipment to move people up and down the face or whatever we may need to do. So wow, this slide looks so much better that you guys fixed it. I think I've talked about this a lot already. The operator in training is the role that I started in. You can become a supervising operator in the field. Authorized nuclear operator is the next role I went to in the control room. There's the fuel handling control room operator I just talked to you guys about, the field supervisor, the control room shift supervisor, and the shift manager. So these are all the different paths you can take. The shift manager supervises about 50 operators, 2 supervisors, every shift that they're in, and they hold the license for the station, which means they're responsible for the safety of the plant, public, and the people, not just on site, but in the surrounding communities. And no one can override them. The CEO, the CNO, the plant manager cannot override the shift manager when it comes to decisions around safety. This is a picture of the Bruce B control room. I'm just going to show you a few pictures of the control room. They're doing a shutdown here. When we shut down, when we do a plant shutdown, we use one of the safety systems so that we can test that it works right. Not because we can shut down easier, but this allows us to test the timing. It takes about 8 years to become a authorized nuclear operator. A couple years in the field, and then 3 years. You can do it shorter, maybe 6. 3 years of training, some co-pilot shifts, a final interview, and then a license from the Canadian Nuclear Safety Commission. That includes some theory, general theory, specific station skills, integrated plant operation, and then simulator skills, which is the most fun. There's some pictures of the Bruce A main control room. This is the common unit. So if I was looking, if I walked in the control room and I'm looking like this is the unit that has the containment, the cooling, the electrical grid, all the stuff that helps all the other units. Over here is unit 3 and 4, and over here is unit 1 and 2. And then in the middle, which I'm gonna get a picture of, is fuel handling. That's another, that's the picture of the reactor unit. From one end to the other, it starts with electrical, goes all the way down turbine generator, boilers, computers, safety systems, and miscellaneous. The computers that run our reactors are 64 kilobytes. That's how old they are. We restart them with a CD-ROM now, but it was a floppy disk when I was first an ANO. And before that, it was tape. So we're still using the same computer to run reactor power, and it works just fine. And you know what? Can't be hacked by cybersecurity. Nobody can get in there. There is an operator watching reactor power here. They just didn't want to be in my picture. That is absolutely happening. So the control room supervisor sits right in front of Gary's face here, and the greatest thing about it is. It's a bit of an elevated platform, so it's like a 2-step stage where your desk is. And then the ANOs are on a 1-step stage, and it really allows you, if you're the control room, that's the person in charge of the control room, that you can hear and see more what's happening all around the room. It's also a little bit like Star Trek, Next Generation, make it so. But it's a really good design that way, and quite often the control room supervisors will hear something before it becomes something, oh, maybe we should look at this, and they're able to go over and assist. Just another picture of the reactor unit, and I think I have a picture. Oh, there's the fuel handling. So this panel right in front of us is being used to move people up and down the face during an outage. There are 3 fueling machines, north, south, and south extension. We're looking right now at the south one. And so we would be fueling units at the same time as we're helping an outage. This is why these fuel handlers are so important. And everything is done in fuel handling in octal, so binary numbers. Like 11 is 3, 100 is 4. And they can read these bits. Like, it's so impressive. I never really got good at it as much as I spent time with them. It's very, very impressive recognition they have for that. Again, though, shows you the design and the age of the plant. We're using little lights flashing on and off in order to move the fueling machines. The simulator that we built for the fuel handling operators to learn from, we could not get the parts for, so we recreated it on a touch screen, and basically you flick the touch screen like you flick the switch in the control room. It's very well done. It's very impressive. But we were not able to find those parts. They are made of what we call in the nuclear industry unobtainium. Here I am showing a picture of SDS2. When SDS2 fires, we have to make sure that all the valves open. We call that a PRAG, Power Reduction Action Guide. And I would be checking for this as soon as a reactor tripped. Even though I'm not a reactor operator anymore, the shift manager does the same. It's another example of the defense in depth. This was an actual Women in Nuclear IWD spread that was put together. And here I am in the control room. That fuel bundle's empty and light. It was ugly sweater day, and since we're hockey fans in Canada, I'm not wearing a soccer jersey or footy. And this is right in front of the control room supervisor desk. The shift manager desk is right around the corner with an open door that you can close. I normally left it open so I could also hear what was happening in there. This was obviously taken a few years ago, and you can see how the desk here is a little further up, a little further back, and kind of looks at the whole control room. And like I say, the shift manager desk is just around the corner, so you can have an opportunity to walk in and check on anything, either in the control room or walk out and check on anything in the field. That's it. All my slides. I don't want to say anything else because there might be a few questions.
What percentage
Hang on a second. All right. Thank you, Tracy. We're now going to go to Q&A. For those in the room, someone will come across with a mic, so please put your hand up if you want to answer, if you want to ask a question. For those of you online, type a question in the Q&A, and someone in the room here will present that for you. So, gentleman up back here.
Yes, I was just going to ask, what percentage of, say, Ontario's power comes out of that one Darlington, I think you called it, nuclear power station, which you worked at?
So 30% of nuclear, of Ontario's power comes from the Bruce, and 30% comes from Darlington and Pickering. So 60% in total is, in Ontario, is nuclear.
Is there only two?
There are 19 reactors in Canada, 18 in Ontario, and 1 in New Brunswick. And that one in New Brunswick is also providing 60% of New Brunswick's power. It's a much smaller province, obviously, than Ontario. So in the nuclear provinces, we are providing the bulk of the power.
Thank you, Tracy. I have a couple of questions online. First one is from Stuart Banks. And with the continuous fuelling, what drives the 3-year outage cycle? What are the main things that need to be done every 3 years?
Mainly, it's reactor inspections. So if we have things that can only be fixed in an outage, like you would here, we will fix them then. But it is the CNSC regulatory requirement that we inspect our boilers, that our feeder tubes, and our feeder cabinets in a certain time frame. That's the driver for the 3 years.
Okay, and the second question, Luigi Sabello is asking around the artificial intelligence. So can you talk a little bit about, you mentioned using sensors before, understanding and feeling how the reactor is operating. Is there any intelligence or sensory type technology that's helping the control room understand reactors?
You know, Ontario Power Generation is doing a lot of this, and one of the things that I think is very helpful is the vibration, remote vibration monitoring, remote breaker monitoring. So if a breaker trips, we can see in the control room what tripped it without sending a field operator to go and verify it, especially if it needs to be done in a timely manner. We can also we can also remotely monitor now temperature changes over time and power. So there are basic gauges at the Bruce and Darlington that, you know, I would say are not really exact, but our engineers now, through this remote monitoring, can pull up, say, the main output transformer and see that every morning when we put a bit more load out, it's going blipping above where it should be and then coming back down. Well, the operators in the control room's not going to see that trend, but so for long-term trending, it's already happening, and there are a couple of really great companies out there that are focused on AI and those changes in definitely in monitoring, more so I would say than control right now. No, yes.
Thank you so much for such an interesting talk, and I really hope one day I can come and see the CANDU reactors and have a good poke around and see what's what. I have a question that is likely naive about the online refueling. When you are refueling online and you, I presume, push the old fuel out the back and then the new comes in the front, do you see a noticeable change in flux as you do that, or is the reactor just so large that there's a sort of, a range of flux that you'll see over time anyway?
That is a great question. So it depends where it is. So we control our reactor power with light water zones in the CANDU. It is a very, very large core, the largest design. But if we are near a zone, where the bundle's near a zone that's controlling flux detectors, we will see that change. However, the reactor responds so quickly to that change by changing the level of light water. It's the tiniest blip. However, our fueling change orders do come with a watch these zones, watch these flux detectors. So we do know where we should be focusing while that bundle's being pushed. And the fuel handling control room operator will say to the ANO, first pair coming through right before they push it, so that the ANO knows to be looking closer at those things. That's a great question.
I've got just two questions, if that's all right. One was, I've read about CANDU and just wanted to know, do you configure it sometimes as a breeder reactor, or is it just power generation?
I mean, I see it as just power generation, but that's been my career. Mm-hmm. We are doing quite a bit of isotopes now. So we've always made cobalt-60 in CANDUs. Now we're making moly, lutetium-177, high specific activity cobalt, and that we're doing that on a lot of those on power. So without having to shut down to remove those isotopes. But that is a new. I mean, it's not our bread and butter, if you know what I mean. It's great, and it's helping the isotope industry, especially in Canada. I really see us more as power generators.
So yeah, you're not making plutonium or anything, okay?
No.
No, that's all right. I was just curious.
We're not allowed to. Well, we are naturally making it. We are naturally making it.
That kind of sucks, because you extend the lifetime of your fuel if you do that.
Yeah.
The other thing I wanted to ask about, so you just, when you've got the spent fuel, you just put it in the casks, or do you do any reprocessing to extract the waste?
We do not at this point.
Yeah.
However, this reactor design I was talking about in New Brunswick, Moltex Energy, that is their plan. They would like to use used CANDU fuel, and they actually have done a test of this at Chalk River Laboratories. Yeah. Reprocess it, use it in their molten salt reactor, and the waste will be reduced by 96% if that works.
Yeah, so it's the New Brunswick reactor, molten salt reactor, that they want to build.
That's correct.
Okay.
There are other ones, but that's just the one I know best because it's in Canada.
Hi. What is your enrichment level of your fuel?
0.
It's not enriched at all?
Not at all. It's natural uranium. We don't even have a processing facility in Canada to enrich fuel.
Okay. With regards to your tritium management, do you run to saturation level? And if so, what changes in reactivity do you get?
I don't think I understand your question.
Pardon?
I don't think I understand your question.
Okay, well, the higher your tritium level goes, you lose reactivity of the core.
No, that's not true. We don't lose any reactivity from creating tritium.
The last question, how much of your isotopes that you hold to hold down the reactivity for your cobalt production, what percentage loss of reactivity?
Oh, that's a good question. And I'm sorry I'm not going to be able to tell you it in millicay, but it's worth about a bundle and a half of fuel, if that makes sense. I can't translate it for you in millicay, but the amount of reactivity that we use to say create cobalt-60 is what we would burn up in a bundle and a half of fuel.
So your cobalt's saturated?
That's correct. And we only take that out when we shut down. We don't remove that on power.
Yeah. Just going back a little bit to your control room. Your control room's got controlling, what, 4 600 megawatt reactors?
900 megawatt.
900 megawatts. So there's four reactors are all on different sides of this control room, aren't they?
Yes.
So everything is quadruplicate, isn't it? So the whole process, what do people deal with more than one reactor?
That's correct. So the way that it works is every reactor has a dedicated authorized nuclear operator, and then there's a spare on each side. And the control room supervisor is in charge of all of those authorized nuclear operators in the control room. So they're like the first line of oversight. The way I put it is the authorized nuclear operator can step on the red carpet. The control room supervisor can stand on the blue carpet, and the shift manager has to be behind the wall. So you have those operators who are in charge of their reactor. The control room supervisor is making sure that they're in the right procedure, maybe asking questions, and the shift manager is back, making sure the whole station is responding appropriately, or if there is an actual transient or an upset. So there's those defense in depth. That defense in depth that's natural really allows you to manage 4 reactors along with fuel handling in the common reactor.
Wonderful, Tracy. You might finish off with 2 more online questions. So Tony Irwin, who's a lecturer at the Australian National University, interested in the qualifications of the control room engineers.
So first of all, you don't have to be an engineer to work in the control room. We do have a lot of engineers, of course, who are interested in becoming operators or shift managers, but it's not a requirement. And that is really because what we're looking for is someone who can learn it and make decisions in the heat of the moment, and be confident in their path forward. So the qualification for authorized nuclear operator is given by the Canadian Nuclear Safety Commission. As I mentioned, it's about a 3-year program. Add another year for control room shift supervisor, shift manager. The control room shift supervisor and shift manager has no more than the reactor units, which is why they do a little bit of extra time, and they have extra simulator training. You get those quals, and in the course of 5 years, you have to retest on everything you got qualified on. So you have to redo the multiple choice written exam. You have to learn all the theory. You have to do a simulator exam again. Every 5 weeks, the entire crew, so my entire crew, would go into the simulator on Monday morning and perform an as found. The ops manager evaluates that, and if my crew did not perform appropriately, we would not be going back to stand watch until we proved that we could. So the certification is hard to get and it's hard to keep, but the training is amazing, and the support we get from the simulator and the training group, really helps us keep those skill levels up. I was licensed for over 15 years, and so you can imagine how many exams I did, and I didn't pass them all. But I went back, redid it before I went back and stood watch again. So that is just, it's just very, very regulated by the commission.
Great. One more online question, and this is from David Collins. So in Canada, you have provinces that are nuclear and others that aren't. Can you make any observations around that? And he's asking lessons for Australia, obviously a non-nuclear power nation.
I think that a lot of it has to do with what's available. So Quebec and Manitoba and BC all have a lot of hydropower, a lot of water. Ontario does too, actually. And so they've not had to really look outside of that. But now Saskatchewan, Alberta, New Brunswick, Nova Scotia have a lot of coal and oil and gas. And those provinces are now looking to nuclear in order to meet their net zero goals. I said this yesterday at my other talk. There's no path to net zero without nuclear. And I feel like not every province or state needs to do it, but those that need to get off coal and cannot fully rely on renewable need to consider it. It might be a small modular reactor. It might be something that is already approved and used somewhere else in the world. Australia doesn't have to, reinvent the wheel. But I definitely think it might not be needed in every state, but I'm sure there are states where it is.
Can you please briefly explain why Ontario went nuclear in the first place, and then how a job in a coal plant might translate to a nuclear plant?
Sure. So I have a great story about this. There's an authorized nuclear operator at Bruce A. His name's Dan Campbell. He worked at Nanticoke, which was a coal plant. And while he was working at Nanticoke, we had hundreds and hundreds of smog days in Toronto. Nanticoke's right basically outside Toronto, in Toronto. And he tells this story about how he was just trying to put food on the plate for his family. Was not tying the running up and down of the coal plant for peak demand to the smog days. When Bruce A, Unit 1 and 2 went through their restart, one came back online in 2012 and one in 2014. The last coal plant shut down, and we haven't had a smog day since. That is because of nuclear. There is hydro in Ontario, but we were not getting off coal unless we refurbed those nuclear plants and were able to provide enough megawatts to the grid. And I will say that's even more true now. With electrification and the needs required as we go forward with vehicles and storage, we're going to need even more power. And it's going to have to come from nuclear.
Well, thank you. That wraps up our event for today.
Yes.
Tracy, my Women in Nuclear sister, it has been really lovely to have you here today to share your story, especially your candid accounts of having to wear men's underwear and pee in the smallest cup on earth for years, right?
Yes, for years.
But that makes change in the long term to make it more inclusive for all of us, no matter what our shape and size is, to work in the nuclear industry. I really love your message as well about how the nuclear community is about sharing. It's not, whilst they are money-making enterprises, ultimately it's about safety so that we can produce power across the globe cleanly but safely. So thank you so much for sharing that. I wish you all the best for your continued journey in Australia. I hope you have a great time here. We've appreciated you coming across to be able to share your experience with us. I'd also like to pass on a huge thank you to the ANSTO crew who helped put this together and the AINSE team for allowing us to use this. The ANA and Win Australia are two small organisations that try to promote nuclear across Australia, and we are working closely together as a community to help share lots of knowledge. So if you're interested, please join our organisations. You can find out about us online. Win Australia is free. ANA, you have to pay a little bit, but it's okay. So thank you to Joe and the ANA for allowing us to co-host this event today. Today is also HIFAR's 65th birthday. Now, Joe had challenged me to sing happy birthday, but I'm not known for singing, so I'm not going to do that. Instead, I'm going to say, hey, happy birthday, HIFAR. Australia's had a nuclear reactor for 65 years, and that's pretty phenomenal. So please, in your own way, have a bit of cake and celebrate for HIFAR today. And finally, before we go, Susan Bogle from the Reconciliation Action Plan out at ANSTO just has one small presentation for Tracy.
Thank you. Hi, and I'll be very quick. So I just, on behalf of ANSTO, I just wanted to extend our deepest thanks to Tracy and her husband David, who gave up 2 days of their precious time in Australia to come and spend with us. Tracy gave an exceptional panel discussion yesterday with Karen Wolfe about helping us on our reconciliation journey here in Australia from some of the learnings with the First Nations people of Canada. So I just want to say thank you so much for sharing your experience, your knowledge, and your cultural identity. It's been a pleasure and an honor to have you here.
Thank you.
You're welcome. Thank you, everyone.
Thank you, everyone.